Hi everyone. Now in today's class we are going to discuss some problems related to limit of a sequence. Okay. Now lecture number 5. So theory number 6, continuation to the last lectures. Theory number 6: if an and bn are two convergent sequences of real numbers which are converging to a and b. Okay. So an converging to a and bn converging to b respectively. Then so first rule, sum rule. Limit n tends to infinity an plus bn. That means you apply limit n tends to infinity to an separately and limit n tends to infinity to bn separately. So that limit n tends to infinity an is a because sequence an converging to a. So therefore the first limit is a and the second limit apply the same limit to second term bn. So limit n tends to infinity bn value capital B. So that's why a plus b. So this rule is called sum rule. Similarly difference rule same. So limit n tends to an minus bn is capital A minus b. And product rule is limit n tends to an into bn. So an is nothing but nth term of the first sequence and bn nth term of the second sequence. Then their limit is product of their limit values a and b, a into b. Fourth one, constant multiple rule. So k is any constant which is a real number and an where an is nth term of the sequence. Then limit n tends to infinity k into an. So k is irrespective of limit because here limit, what is variable? N is a variable. So therefore n terms you have to keep inside, remaining terms you have to send outside. Therefore you send k outside. So then what happens? K into limit n tends to infinity an. But what is limit n tends to infinity an? Which is capital A. That's why k into a, where k is constant. Of course you can keep k is a complex number also, no problem, for some constant k. Okay. Quotient rule. Limit n tends to infinity an upon bn is nothing but a upon b provided b not equal to 0. If b is equal to 0 then this term is undefined. Some finite number upon 0 is infinity. So which is undefined. That's why b should not be equal to 0. Then only this one is makes sense. So this is some one basic theorem before entering into finding the limit of a sequence. Now let us enter the problems. So problem number 1 is the sequence decreasing. The sequence is decreasing. If so, find its least upper bound, LUB or supremum. So first, is it decreasing? So the given sequence in which nth term is 3n plus 4 upon 2n plus 1. So without finding the terms of this sequence, how to investigate the decreasing and increasing of a sequence? You can look at like this. You can do like this. So an is this, therefore what is an plus 1? So find out both the terms an and an plus 1. So then wherever n, there you keep n plus 1. So 3 into n plus 1, 3 into n plus 1 plus 4 upon 2 into n plus 1 plus 1. Okay. Then simplify this, you'll get 3n plus 3, so 7. So 3n plus 7, 3n plus 7 upon and 2n plus 2, so 2n plus 3, 2n plus 3. Okay. So this is an and an plus 1. Now let us find this difference. What is the value of an minus 1? An plus 1. Sorry, an minus an plus. That means we are subtracting an plus 1 from an. So 3n plus 4. Okay. Just I want to investigate this sign an minus an plus 1. If an minus an plus 1 is more than or equal to 0, then an is more than or equal to an plus 1. Therefore, it is decreasing sequence like that. Okay, if it is less than 0, it is increasing sequence like that. So 3n plus 4 upon 2n plus 1, okay, minus and an plus 1 value 3n plus 7 or 3n plus 7 upon 2n plus 3, 2n plus 3. Now find out the LCM is, what is LCM? 2n plus 1, 2n plus 1 into 2n plus 3. Okay, 2n plus 1 into 2n plus 3. This is LCM. And do the cross product. So 3n plus 1 into 2n plus 3. So 3n plus 4, 3n plus 4 into 2n plus 3. Actually, this is a standard method or procedure for finding whether the sequence is increasing or decreasing like that. Okay. So now 3n plus 7 into 2n plus 1. 2n plus 1. Okay. So now simplify the terms. So 3n into 2n, total 6n square. Okay, 6n square. 3n plus 3 plus 9, 9n. 9n plus 4 to the 8n. How much? 17n. Okay, 17n. Next, 4 3 is a 12 plus 12. Okay, look at once again. 3n into 2n, 6n square. This is 6n square. And after that, 4 into 2, 8n, and plus 9n, 17n, and 4th is a 12, minus same thing. What is the denominator? 2n plus 1. So 2n plus 1 into 2n plus 3. 2n plus 3. So now simplify this. So 6n square minus 6n square out. 17n plus 17n is out. 12 minus 3. How much? 9, right? So 9 upon 2n plus 1 into 2n plus 3. Okay. So I think this is 7, right? 7 minus 7. Yeah. This is minus 7. Minus 7. So 12 minus 7 is, this is, yeah, whatever. But just I want the sign only. So 12 minus 7, it is 5. So it is 5. Now here, what is n? N belongs to natural number set, right? So n is a natural number set, therefore 2n plus 1 is never negative. 2n plus 3 value is also never negative. Okay. Then 5 upon 2n plus 1 into 2n plus 3 is always equal to or more than equal to 0, because it is never negative, right? 5 is positive, and since n is natural number, since n belongs to natural number set, this never negative and this one also never negative. So these two are positive terms. Product of positive term is positive. So positive term divided by positive term is again positive. Therefore it is more than equal to 0. So therefore final conclusion is, so therefore I arrived like this: an minus an plus 1, an plus 1 is more than or equal to 0 I got. So therefore I can say that an is more than or equals to an plus 1. So therefore what kind of sequence it is? So clearly, so therefore the sequence, the given sequence an, which is 3n plus 4, 3n plus 4 upon 2n plus 1 is what kind of sequence it is? This is decreasing sequence. Decreasing sequence. Decreasing sequence. So once is over. So decreasing sequence is over. It is decreasing. If so, question. Look at the question. If so, find its least upper bound, that or supremum. So once it is decreasing sequence, so it means this, it means substitute 1. So a1 is more than or equals to a2, and a2 is more than or equals to a3. a3 is more than or equals to a4, is more than or equals to a5, plus up to so on. Sorry, up to so on. So this is what is meant by decreasing sequence. Okay. Now in this pattern, what I want supremum, least upper bound. Least upper bound means I need to find an which is bounded above, right? Bounded above by some number. So this number m is called upper bound. I need to collect all such upper bounds. Okay. In that upper bounds, what I want? Least one I want. That is called supremum. Okay. Now in this, what is the supremum now? The term a1 become the least upper bound. Already we discussed this one in the last class. Therefore here a1 becomes least upper bound. So therefore here I can say that clearly an is less than or equal to a1. It is true for all n belongs to natural number set for such kind of decreasing sequences, right? Because a1 is the highest term compared to all the terms. Therefore each and every term is below by a1. So therefore a1 becomes least upper bound. So therefore here what is a1? So therefore clearly, so therefore a1 is simply substitute n is equal to 1 in nth term of the sequence. Here look at, this is an, n is 1, 7 by 3. So n is 1, so 3 plus 4 by 2 plus 1, 2 plus 1, which is 7 by 3. So therefore LUB, least upper bound, is 7 by 3. That's it. So therefore I can say that now each and every term of the sequence n is less than or equal to 7 by 3. That's it. It is true for all n. N belongs to natural number set. Whatever the term you take, whatever n you take, each and every n, that will be bounded below by 7 by 3. Therefore 7 by 3 set is supremum. Okay. Next, problem number 2. Yeah. Show that the sequence is bounded. So sequence is bounded. It means I need to find a small m and capital M, lower bound or upper bound. That means I need to find a small m less than or equal to a n less than or equal to capital M. So these both capital M and small m I need to calculate. If both small m and capital M are existing, then I can say that the corresponding sequence a n is bounded sequence. Okay. Now let us find such a small m and capital M here. So now the given sequence is, so therefore, so first nth term of the sequence a n is 2 minus 1 upon 2 to the power of n minus 1. Okay. So just by there are two ways to attack this problem. Simply I need to find lower bound and upper bound. Okay. Look at here, as n belongs to natural number set. N belongs to natural number set. That means n is 1. If substitute n is 1, you will get 1 minus 1 0. 2 power 0 is 1. So 1 by 1. So 2 minus 1 is 1. So first term is 1. A1 is 1. What is second term? A2. Substitute n is 2 here. So 1 by 2. 2 minus 1 by 2. Next 2 minus 1 by 4. Next 2 minus 1 by 8. 2 minus 1 by 16. So every time you are subtracting one positive number which is less than 1. So this is a positive number which is less than or equal to 1. Okay. So this is a positive number. This one is less than or equal to 1, right? Particularly always less than or equal to 1 for all n belongs to natural number set. Okay. So this is always less than or equal to 1, this number, this quantity. Now 2 minus a number which is less than 1 is always positive. Okay. So therefore I can say that by this observation, so therefore since n belongs to natural number set, I can say that 1 upon 2 over n minus 1, 1 upon 2 raised n minus 1 is always less than or equal to 1. Okay. Once it is less than or equal to 1, so therefore an, so which is 2 minus 1 upon 2 raised n minus 1 is always less than or equals to what? I can write 2. So whatever the term you take here for n value, each and every term is less than or equals to 2. So therefore indirectly I found the upper bound. Indirectly capital M is 2 here. So therefore such a number capital M is existed here. So M is 2. Upper bound is existed, right? Similarly lower bound also, look at, since an, so an which is 2 minus 1 upon 2 raised n minus 1, this is never negative, right? This is always more than or equal to 0. It is never negative because a number, this one is a number you are which is less than 2, right? This is always less than 2. In fact it is less than or equal to 1 only, right? So it's always less than 2. You are subtracting a number which is less than 2 from 2, therefore it is always more than or equal to 0. It never be negative. So therefore this is the lower bound. So therefore clearly I can say that. So let us take this is 1 and this is 2. From both the inequalities from 1 and 2, so from 1 and 2 I can say that from 1 and 2, what is the conclusion? So from 1 and 2 I can say that, so an which is 2 minus 1 raised 1 upon 2 raised n minus 1 is bounded above by 2 and bounded below by 0. So it is like small m and this is like capital M. So such upper bound and lower bound existed, therefore the given sequence is bounded. So therefore the sequence 2 minus 1 upon 2 raised n minus 1 is bounded sequence. Okay. Next, what else we need to find? Also find its least upper bound or supremum. I want its supremum. Okay, how to find supremum? So we need to find all the upper bounds. In that, the least one we have to pick up. So in fact I can write 2, it is less than or equal to 3 also correct, less than or equal to 4 also correct. So a number which is more than 2 is also an upper bound, but before that a number which is less than 2, can it be an upper bound? We need to calculate. For example, 1.9 you take. Okay, 1.9 is less than 2, does it be an upper bound? For example, if it is an upper bound 1.9, 2 is also an upper bound. In this 2, which is least one? 1.9 is the least one, therefore this become supremum. For example, let us take 1.8. If 1.8 also an upper bound, then done. 1.8 is upper bound, 1.9 is upper bound, 2 is an upper bound, but the least one is 1.8, therefore 1.8 becomes supremum or least upper bound. We need to collect all upper bounds, in which least one we have to collect. That is called, look at here, least upper bound, right? So therefore, we need to investigate whether does a number less than 2 exist, which is an upper bound. Okay. So before that, at what number the sequence converges, you calculate. So limit n tends to infinity, an nth term. So limit n tends to infinity, n tends to infinity, 2 minus 1 upon 2 raised n minus 1. Okay. So this is, so by using difference rule, so limit n tends to infinity to n, limit n tends to infinity 2 minus limit n tends to infinity 1 upon 2 raised n minus 1. Okay. Now limit n tends to infinity 2 is 2 itself, that's it, because there is no n here, minus limit n tends to infinity 1 upon 2 raised infinity minus 1, which is 2 minus 0, which is 2. So the sequence is converging to 2. So the sequence is converging to 2. Now can I say that this is the least upper bound? Before that, I want, if a sequence is an increasing sequence, if the sequence is increasing sequence which is bounded above, look at the theorem number 5 which was discussed in the last class. If you have an increasing sequence which is bounded above, clearly it is bounded above because look at here, 2 existed, upper bound is 2, right? So clearly it is bounded above sequence. And if you show that if it is an increasing sequence, so an increasing sequence which is bounded above is always converges to its least upper bound, that is called supremum. Therefore now I can conclude that 2 is a supremum, but here I don't know whether this sequence is increasing sequence or not. Until unless it is not increasing sequence, you cannot conclude 2 will be an supremum. Okay, for example, look at this best example. See, for example, you take 1 plus 1 by n. At what number the sequence converges? Clearly it converges to, let us take this sequence, and this sequence is converges to 1, right? After limit n tends to infinity, you will get 1 plus 0, 1. If you take 1 minus 1 by n, at what number the sequence converges? It is converges to 1 only. But you look at for this sequence, what is the first term? First term will be 0. First term 0 because substitute n is 1. Second term half. Third term 1 minus 1 by 3, 2 by 3. Next, fourth term 1 by 4, so 3 by 4. What kind of sequence it is? It is increasing sequence, right? So this is an increasing sequence. Okay, now this is converging to 1. So last one is 1. If it is an increasing sequence, I can say that the converging point is nothing but supremum. But what about this one? It is 2. First term is 2. Substitute n is 1. N is 2. 1 plus half, 3 by 2. It is decreasing sequence. It is converging to 1. Now can I say that this 1 is a supremum? No. Here what is a supremum? 2 is a supremum. Okay. So 2 is a supremum. So immediately I cannot say that the limit point will be the supremum. Here limit point is 1, here limit point is 1. But in this case the limit point 1 I can say supremum. But in this case the limit case 1 cannot be a supremum because here 2 is a supremum. Okay. So therefore, if you don't know the sequence is not increasing or decreasing, you cannot say that limit point will be the supremum. So let us find where the sequence is increasing or not. If it is increasing, then we are done. Okay, yeah, let us find out what kind of sequence it is. So then it an minus an plus 1. What is an? 2 minus 1 upon 2 raised n minus 1 will be an. Okay, this is an minus an plus 1. 2 minus wherever n, there you write n plus 1. 1 upon 2 raised n. Instead of n I am writing n plus 1, so minus 1 plus 1 cancel out. Now here 2 cancel out, 2 minus 2 cancel out, and what is left? 1 over 1 upon 2 raised n minus 1 upon 2 raised n minus 1. Okay, this is an minus an plus 1. Is it more than or equal to 0 or less than or equal to 0? So before that, 2 power n is always more than or equal to 2 power n minus 1, right? You take for any natural number, if I substitute n is 1, what will you get? 2 power 1 is 2. Here 2 power 0 is 1. So 2 is more than or equals to 1, correct? Substitute n is 2. LHS is 4. RHS is 2, correct? N is 3, 8, 4. So it is true for all n belongs to natural number set. Then after that, you reciprocal this. 1 upon 2 raised n is less than or equal to 1 upon 2 raised n minus 1. I am reciprocaling the numbers. Therefore, inequality will change. So therefore, 1 upon 2 raised n minus 1 will be always more than. So therefore, clearly I can say that from here I can say that 1 upon 2 raised n minus 1 upon 2 raised n minus 1. Then send this term to this side. This term send it to LHS side. What will you get? Less than or equal to 0. Therefore, what is this sign? It is less than or equal to 0. So because of this investigation. So now this one is less than or equal to 0. So therefore clearly, so therefore I can say that an minus an plus 1 is less than or equal to 0. So therefore I can say that an less than or equal to an plus 1. So therefore it is an increasing sequence for all n belongs to natural number set. So therefore the sequence an is nothing but 2 minus 1 upon 2 raised n minus 1 is an increasing sequence. An increasing sequence. Increasing sequence. So once it is increasing sequence, so it is an increasing sequence is over, and also which is bounded above, bounded above by which number? Bounded above by the number 2. Okay, therefore what is the conclusion? Therefore by theorem number 5, the sequence two minus 1 upon 2 raised n minus 1 is converges to its supremum. In theorem number 5, you look at the note. In the note, I have written it's supremum. So therefore, what is supremum? Supremum of 2 minus 1 upon 2 raised n minus 1 is its converging point. But what its converging point? Just now we calculated its limit. Look at its limit is how much? 2. So 2 is the limit, right? So therefore its supremum is 2. So this is the supremum. That's what the question, right? So that is bounded, and also find its least upper bound or supremum. That's it. Next, problem number 3. Find the limit of the sequence. So yeah, so let assume the given sequence an is 3 plus 2 into n raised 4 upon n raised 4 minus 8. Okay, then take out nth term of the sequence an, which is 3 plus 2 into n raised 4 upon n raised 4 minus 8. Okay, then apply limit. So limit n tends to infinity an, which is limit n tends to infinity. What is an? 3 plus 2 n raised 4, 2 into n raised 4 upon n raised 4 minus 8. So now which is, yeah, so before applying to limit, let us take out the common, the highest power of n you should take out. Limit n becomes large. So in the numerator I am taking n power 4 is common. So if you take n power 4 is common here, you will get 3 upon n raised 4. Okay, 3 upon n raised 4 plus 2. This is the numerator term divided by denominator term also. You take n raised 4 common. 1 minus 8 upon n raised 4. Okay. Now, why I am taking n power 4 is common? There is a fundamental question. If you don't want to take n power 4 as a common, then what happens? You apply the limit n tends to infinity. What will you get? 3 plus 2 into infinity power 4. You will get numerator value is infinity. Now, what about denominator value? Infinity power 4 minus 8 is again infinity. Infinity by infinity you will get, but this is indeterminate form. You cannot find this value. Okay, indeterminate. Sometimes it can be determined, sometimes it cannot be determined. That is called indeterminate form. So then you want to determine the limit first. So that's why we want to overcome this difficulty, infinity by infinity. That's why we are taking n power 4 is common, so that we can apply the limit easily. We can find the limit easily. Okay. Now, yeah, apply limit now. 3 upon infinity now. Look at limit n tends to infinity, 3 upon infinity plus 2 divided by 1 minus 8 upon infinity. Okay, so which is 0 plus 2 divided by 1 minus 0. So answer is 2. So therefore the given sequence, which is 3 plus 2 n power 4 upon n power 4 minus 8, n power 4 minus 8, this one is converges to number 2 as n tends to infinity. So the given sequence converges to 2. Okay, next one. Problem number 4. Find the converging point of the sequence. So again same ideology. Solution. Yeah. So directly I am writing. So limit n tends to infinity an, nth term of the sequence. So limit n tends to infinity. What is an? So this is an. So this term is an. Okay. Root over n upon 2n minus 1. So this is nth term of the sequence. Okay, that is nth term of the sequence. So then you apply the limit. What happens here? If you apply the limit, again you will get infinity by infinity form, right? Then you overcome the difficulty, then take out n common from the numerator and n common from the denominator. Okay, so if you take out n common from the numerator, inside you take out inside n upon, here I am taking n from denominator, so n is out, so 2 minus 1 by n. Okay, so now what happens? N cancel out, this n cancel out. Okay, what is left? Only numerator 1 is left. So therefore after applying limit you will get square root over 1 upon 2 minus 1 by infinity you will get. It means simply square root over 1 upon 2. This is simply 1 by root 2. So this is the limit of the sequence. So therefore the given sequence converges to 1 by root 2. So therefore I can write, therefore the given sequence 1 by root 2. 1 by root 2. Okay, next one. Problem number 5. Yeah, this one, how to attack this problem. Again same, so assume the given sequence which is an, this is a square root over n raised 2 plus n. square root is only for n square plus n only and minus n. So this is a given sequence, and at what number this sequence converges? So limit n becomes large, or limit n tends to infinity, whatever. Now limit n becomes large, n square plus n, which is in the square root, minus n. So if you apply the limit directly, what you will get? So apply the limit, you will get infinity, because square root over infinity square plus infinity is infinity only. Root infinity is infinity, minus infinity. Infinity minus infinity, don't say it is 0. This is wrong. Okay, this is absolutely wrong. This is indeterminate, undetermined. This is infinity minus infinity is undetermined. How it is undetermined? See, infinity means, what does it mean by infinity? Infinity is also infinity. It is not a number. First of all, it is the representation for a huge quantity. It is the representation for huge quantity. For example, I will explain geometrically, then definitely will accept infinity minus infinity is not equal to 0. Look at that. Look at here. For example, I have taken two rocks. Two rocks I have taken. Now I am counting number of atoms here in this rock. I'm counting number of atoms. Number of atoms. How many? Can you guess? Number of atoms in this rock. How many? Infinity, right? Now in this rock again, number of atoms. Same question. Can you find number of atoms? Again infinity, right? It doesn't mean that both the infinities are same. Look at geometrically, this was very big, right? Therefore number of atoms will be more than this number of atoms compared to the first rock. Therefore here the number of atoms are more, but we don't know. That's why we are giving the representation infinity to that number of atoms. So therefore what is now infinity minus infinity? Can I say it is 0? So number of atoms from this rock minus number of atoms to this rock, can I say it is 0? No, it is not equal to 0, right? That's what I'm telling. Just it is representation of huge quantity, that's it. It is not a number. So therefore infinity minus infinity, you cannot say it is 0. You cannot find its value first of all. Okay, that's why I should not apply directly. Then if you are getting indeterminate form, then what to do? So take common, you have to cancel out, but it is not a fraction. Look at the previous problem. Square root over n upon n plus 1 I have taken. So n I have taken common, I cancelled out because it is a fraction, but here it is not a fraction. Then what to do? The trick is you rationalize it. Okay, so limit n tends to infinity, and what rationalize this? What is the rationalizing factor of this? N square plus n minus n. What is the rationalizing factor of this? Rationalizing factor of this one is n square plus n, here minus, right? So plus n. So with that you multiply and divide. Okay, you multiply and divide. Okay, so yeah, then what do you get? So limit n becomes large. Yeah, simplify this. A minus b into a plus b, a square minus b square. So root square root will cancel out, n square plus n, but here minus n square will get, right? Minus n square upon denominator n square plus n, n square plus n plus n. Okay, now so yeah, cancel out the similar terms. N square minus n square cancel out, only numerator n remains. So limit n becomes large. Limit n becomes large. Numerator was n upon denominator. You take out n square is common from the square root. So if you take n square common, you get 1 plus 1 upon n, right? 1 plus 1 upon n inside and outside n. Okay, yeah. What will you get now? Limit n becomes large. N becomes large. So numerator was n, and the denominator from inside the square root, if n square is coming out, what will comes out? N will comes out, right? Because it is under square root. So 1 plus 1 upon n. Okay. So inside n square, this n square I am dragging out, it comes out as n because it is under square root, and plus n is outside. So now overall you take out from the denominator n common. So then it becomes limit n becomes large. Limit n becomes large. From the numerator n as it is, denominator n common. So inside is a square root over 1 plus 1 upon n, 1 plus 1 upon n plus 1, because you have taken out n is common. So now this n, numerator n cancelled out with the denominator n. Okay. So what will remain? So now limit n becomes large. You apply the limit, so 1 upon square root over, so 1 plus 1 upon infinity. Okay, and plus 1. What will you get? Which is 1 upon root 1 plus 1. Nothing but 1 by 2. So therefore the given sequence which converges to 1 by 2. Next one, problem number 7. Find the limit of this sequence. Okay, so now limit n becomes large, an, which is limit n becomes large, n raise 1 upon n. Okay, and now here apply limit directly infinity to the power of 0 you will get. What is the value of infinity to the power of 0? Again we can't determine this, so therefore directly another method I need to approach. Why another method? Therefore I am approaching like this. So let us take, so if you are applying directly n times infinity, if you are getting value, for example, let's say 2 power n you are having, for example 2 power n is the nth term, n is 2 power n. Now you apply limit n times infinity, what will you get? 2 power infinity. This direct answer is infinity only. Perfect, no problem. Then you write directly. But here it is not like that. If you are applying limit n times infinity to direct to this function, you are getting infinity power 0, but this value we cannot determine. That's why we are not applying directly limit. Then we need to adopt some other techniques. So I want to adopt this technique. So let an is, so nth term of the sequence is n raise 1 upon n, n raise 1 upon n. Now apply ln both sides. Apply natural logarithmic function both sides. ln function. Apply ln function both sides. Both sides. Then what will you get? ln an is equals to ln n raise 1 upon n. Okay. Now this is ln an is equals to, this will become 1 upon n into ln n. Look at the properties of natural logarithmic function. So ln of a power b becomes b into ln a, right? By using this formula, this 1 upon n will come down. So 1 upon n into ln n. Okay. Now this is ln n by n. It's like previous problem only. ln n by n. Now this is ln an. Now you apply limit n tends to infinity both sides. Okay. So limit n tends to infinity ln an, right? ln an is equals to limit n tends to infinity. Both sides I am applying limit here from this step. Okay. Ln n upon n. Again you apply limit, you will get again infinity by infinity form. If you are getting infinity by infinity form, what to do in general? In general, either L'Hospital rule I can proceed, or by this is one of the technique. Either we can function natural logarithm function, but already applied natural logarithm function. So then go to the L'Hospital rule, whether it is work out or not. Okay. Here, why don't I apply L'Hospital rule? Because it is not in the form of 0 by 0. Look at it is infinity power 0 I got. If you are getting 0 by 0 or infinity by infinity, then only you go to the L'Hospital rule. Okay. But it is not like that. But here you are getting infinity by infinity form, then go to L'Hospital rule. Yeah. Then limit n becomes large. Limit n becomes large. What is ln n derivative? 1 by n, and nth derivative n derivative 1. Okay, separate differentiation is over. Next, this value is 0. Just now we calculated. So therefore, what I got, so limit, problem is not over. So limit n tends to infinity, ln an value is 0. Okay, but what I want, limit n tends to infinity, an value I want, right? This value I want. Look at first step. Limit n tends to infinity, an value I want, but limit n tends to infinity, ln an value I got. So therefore, here I can write. So therefore, limit n tends to infinity, an value. That means ln I am sending to this side. So here nothing is there means base e, right? Natural logarithm function base e. So e will goes this side, it becomes e power 0. Okay. So therefore this become limit. See, this step is obtained from this step only. Okay, this base is sending this side, so e raised 0 I will get, and this side only an remains. So therefore limit n tends to infinity, an is equal to e raised 0, which is 1. Therefore now the given sequence converges to 1. So therefore final conclusion, sequence n raised 1 upon n, n raised 1 upon n converges to which number? 1. 1 as n tends to infinity. N tends to infinity. Okay. Next one. Problem number 8. Find the converging point of a sequence nth root of 4th power 4 raised n into n. So an, nth term of the sequence is nth root of 4 raised n into n. Okay, simplify this. What will you get? 4 raised n into n whole raised, nth root means it is 1 upon n, right? 1 upon n. Now apply separately. So 4 raised n to the raise 1 upon n into this 1 upon n to the, this 1 upon n is the power for both the numbers, right? 4 power n and n. That's what I am applying. So n power 1 by n. It's like, 2 into 3 power 2. What is this? 2 raised 2 into 3 raised 2. Okay, like that. 2 into 3 or 6 raised to 36, like that. So you are applying power to the both the numbers separately. Same like that what I have done. And now what is this? 4 into, because n into n cancel out, only 4 will remain, into n raised 1 upon n. So this is an now. This is simplified an. Now let us apply the limit. Now limit n tends to infinity, an is equals to limit n tends to infinity 4 into n raised 1 upon n. So this is constant multiple rule. By using constant multiple rule, by using theorem number 6, today's theorem. So 4 is constant, you can drag out, because that is irrespective of limit, because limit is only for n terms which are involved n only, because limit n tends to infinity. So n raised 1 upon n. 4 I have dragged out. Okay. Now in this, look at n raised 1 upon n value. How much it is? Just now we did. This value is 1. Okay. So directly I am writing. So if you don't know, see, for example, if this is a problem which came in exam, what to do? You have to calculate this value. Take this separately. Let us assume this is some bn like this. So let bn is n raised 1 upon n. Then apply ln both sides. Ln bn is equals to ln of n raised 1 upon n, like this. Then proceed. You will get this value, limit of this value. Then substitute here like that. Okay. So here directly I am writing. So this value is 1. So therefore final answer is 4. Therefore the sequence is converges to 4. So therefore conclusion tends to infinity. See, what is meant by converging to 4? So many students are asking, so what is meant by converging to 4? Converging to 4 means, see, once again I am telling, already told in my first class. See, for example, an is a sequence. Okay, a1 is the first term, a2 is the second term, a3 is the third term, up to so on, up to so on. So these are the terms of the sequence. So this is the second term, second position term a2, third position term a3, fourth position term a4. Likewise, what is the number which is at infinite position? You cannot go for, first of all, at that infinite position. The infinite is a large number. You cannot go to that number. Without going to that position, what is the number. So that is called converging point. Okay, converging, that means what, reaching to that number. So therefore the sequence reaching to 4 as n becomes large means what, if n is 1 first position, second position, n is 2 second position, n is 3 third position, n is 4 fourth position, likewise as n becomes very large, that means if you go into a large numbered position, what will be the number at that position? So number will be 4 at that position. So that is a hidden meaning of converging of a sequence, converging point of a sequence. Okay, so therefore this sequence converging to 4 as n becomes large. So this is 8th one. Next one, 9th problem. Yeah, again same problem. See, I have taken different problems from different areas. Yeah, so limit n becomes large an, so which is limit n becomes large, n plus 2 upon n raise n. Okay, so now this is limit n tends to infinity, yeah, let us separate this. So n by n, that is 1 plus 2 by n whole raise n. What is this value? Directly, if you know the formula, you can write it. So I'm writing the formula. Since by formula you have seen this one in PUC, what is that? So limit n tends to infinity 1 plus x by n whole raise n. What is this value? Can you guess, anybody? Limit n tends to infinity, look at, only n is a variable here, so x is any number, so this will be e power x, so by using this formula, this one directly I can write, so which is now, so by using this formula, what is this value now? So therefore this value is e power 2 only, because instead of x we are having 2, so therefore e power 2. So without using this formula, how to find it? Simply, so second method, you take it exercise, I will give the hint. Second method, okay, this is second method, so this is first method. How to find the limit by using second method? So first you take, so let an is 1 plus 2 by n whole to the power of n first. Let us take, this is your an, right? This is your an. Then apply both sides ln, natural logarithm function, both sides. So then n will come down, ln of 1 plus 2 by n, like this, 2 by n. So next step you take, this is ln of n plus, so simplify this, n plus 2 by n, n plus 2 by n divided by n, I can write 1 by n, right? 1 by n. Now it is a fraction kind of. Now you apply limit n tends to infinity here. What happens now? Infinity by what do you get? Yeah, you can keep like this, no problem. Apply limit, what you will get? ln1, right? ln1 is 0, 0 by 0 form you will get. Then go to the L'Hospital rule. Numerator separate differentiation and denominator separate differentiation. So this is a technique you apply. So then you will get e power x formula. So this is a proof of limit n tends to be 1 plus x by n whole power n, which is e power x. So try in this way, you will get e square. This is the second method. Try once. Okay. So this is directly by using formula. Next one, problem number 10. So again find the limit point of the sequence. So limit n tends to infinity an, which is limit n tends to infinity n plus 1 by n minus 1 whole raise n. Okay. Now, so I want to modify this. Look at carefully how I am modifying. So if I apply directly n tends to infinity, what happens? Infinity plus 1 is infinity, divided by infinity minus 1 is infinity. So I will get infinity by infinity power infinity. Don't cancel out infinity ones are infinity ones are. That is wrong. Just now I told you already. These two infinities are not same. They may not be same. right? It is a representation for huge quantity. So finally what I will get? Indeterminate form I will get. I am getting indeterminate form. So therefore direct limit application is not useful here. So don't apply directly. Then we have to apply some technique here. So what I am doing is, look at inside carefully. Inside one, you take n common from the numerator. What will you get? 1 plus 1 by n. 1 plus 1 by n. Similarly, from the denominator, n is common, 1 minus 1 by n. Okay, just one n I have taken common from the inside. Then next step, limit n becomes large. Okay, so these two n's cancel out, right? Now what happens? 1 plus 1 by n, 1 plus 1 by n, and I am applying the power separately. Numerator power n and denominator 1 minus 1 by n separate. Okay, so I am applying the limit intensity to this entire term. So this is nothing but it means limit can be applied both numerator and denominator separately. 1 plus 1 upon n power n, okay, divided by limit n tends to infinity. This is by quotient rule. Look at theorem number 6, today's theorem. By quotient rule I am doing this. Again by the formula just now I quoted. So this will be e power x. Instead of x what you are having? 1, right? Instead of x you are having 1. Again I am quoting here the formula. What is the formula? Limit n tends to infinity 1 plus x by n power n. This will be e power x. So since by using this formula, what is this? E power 1. Numerator value is e power 1. Denominator value e to the power of, instead of x you are having minus 1. Write this one as plus minus 1 like this. So plus, here you write plus and here you write minus. So instead of x you are having minus 1. So minus 1. So overall it will be e square. So final answer is e square. Therefore the given sequence converges to e square. Okay. So this is first method. You can do it by second method also. I'll give the hint. Again you try. So this is by first method. Let us do it by second method. Method number 2. Second method. In this, so what is an? An is n plus 1 by n minus 1 whole to the power of n, right? Again here you apply nature logarithm both sides. So this is the second method. So if I apply nature logarithm here, you will get n into ln of n minus 1 by n plus 1 by n minus 1. Okay, so then after that, yeah, then simplify this. Ln an is equals to ln n plus 1 by n minus 1, okay, divided by 1 by n I am getting. Write this n as 1 by n, this n come down as 1 by n. Now here if you apply limit, what will you get? So limit, let me do it, at the end I will give you the exercise. Ln an, so limit n tends to infinity, yeah, look at the numerator, ln of n plus 1 by n minus 1, okay, divided by 1 by n, okay. And now you apply limit, what you are getting. So if you apply the limit here, look at, you take n common from the numerator. If you take n common, what happens? 1 plus 1 by n, right? So here 1 plus 1 by n will get 1 plus 1 by n, and denominator also 1 n common, so 1 minus 1 by n. So this is ln of, right? This is ln of. In this function, inside n I am taking common from the numerator and denominator, that n will out, and 1 plus 1 by n, 1 minus 1 by n. Now apply limit n tends to infinity. What will you get? Ln of 1 by 1, ln 1 you will get, that means 0 you will get, 0 by 1 by infinity is 0. So 0 by 0 form you are getting. This is indeterminate form, therefore go to L'Hospital rule. Okay. Then L'Hospital rule, numerator differentiation separately and denominator differentiation separately, like that. Okay. Proceed this, differentiate this one separately and differentiate this one separately, then apply limit n tends to infinity. Again if you are getting same format 0 by 0 or infinity by infinity, then again go to the L'Hospital until you will get a proper limit value. Take it exercise. Okay, take it exercise. Try this. Okay, next one, 11th one is some another one. Again, we want the limit value of this sequence. Okay, if the sequence defined by a1 is root 2 and next it is a recursive sequence, an plus 1 is this. So a1 is root 2. Okay, what is a2? How to get a2? Substitute here n is 1. If n is 1, if n is equal to 1, you will get a2 value. What is that a2? a2 is square root over 2 plus a1, right? Which is nothing but square root over 2 plus root 2. This problem I have done in the last class, but I have taken c here. a1 is root c and an plus 1 is equal to c plus an I have taken. Just recall. Next substitute n is 2. What will you get? a3 value. What will you get? 2 plus n is 2, right? Substitute here a2. a2. What will you get? Square root over 2 plus what is a2? a2 value is square root over 2 plus root 2. So this is a2. So like this you will get. So overall therefore the sequence, the given sequence an will be the what will you get? Root 2 square root over 2 plus root 2, okay, comma square root over 2 plus root 2, like this. So up to so on. So this is a given sequence. At what number the sequence converges? Already given that if it is converges, look at here question. If the sequence is converges, then find its limit. It is converges. So you look at one of the theorems what we discussed in the last classes. For example, just quickly recall. If an is converges, for example, if an sequence an converges to L, okay, and you take two subsequences, a2n plus 1 is one subsequence and a2n is another subsequence, or two subsequences, two subsequences of an. Okay, then what can you say about these two subsequences? Then what I can say, then the two subsequences a2n plus 1, this one converges to same limit L, right? And another subsequence a2n is also converges to L. Look at one of the theorems what we discussed. If a sequence is converging to L, then you take any two subsequences of that subsequence also converges to the same limit. Okay, by using this concept, I want to find the limit of this sequence. Okay, so let me write, that is, so limit n tends to infinity, a2n plus 1 value is L. Converging to L means what? Limit value is L, and limit n tends to infinity, a2n value is L. If limit n tends to infinity, an value is L. Okay, so by using this concept, let me write this again. So an plus 1, so limit n tends to infinity, an plus 1, or before writing the limit, first let me write what is the recursive sequence. An plus 1 is equals to square root over 2 plus an. So this is how to find a limit for the some kind of recursive sequence, particularly this kind of problems. Okay, now apply limit both sides. Apply limit as n tends to infinity both sides. Then what will you get? So limit n tends to infinity, an plus 1 is equals to limit n tends to infinity square root over 2 plus an. Okay, now here you should be little cautious. So this become limit n tends to infinity, listen carefully, an plus 1 is equals to, let us take limit inside, so square root over 2 plus limit n tends to infinity 2 values 2 only, and limit will be applied here, limit n tends to infinity an. Okay, but now go back to the question. What is the question here? If the sequence is converges, if the sequence is converges, then find the limit. Already given that the sequence is converges. So once the sequence is converges, so the sequence, let's say it's converging to L. That means what? Limit n tends to infinity an is L directly. Okay, then you take any two subsequences, that two subsequence also converges to same limit L. So by this concept here, what I can say is, let's say this value is L, limit n tends to an plus 1 is L, so which is 2 plus this is also L because it is converging sequence. So an plus 1 is one of the subsequence, right? N plus 1th term of the subsequence an plus 1. So this is nth term of the sequence. So both will converge to the same limit L only because it is converging sequence. So by using this, so this step is crucial now. Okay, now square on both sides, you will get L square is equal to 2 plus L. Okay, now L square minus L minus 2 equal to 0. Then you apply, for finding L value, you apply minus b plus or minus b square minus 4ac formula. So plus 1 minus or minus plus 1 plus or minus b square 1 minus 4ac. So minus or minus plus 4 to the 8 by 2 into a 2. So what you will get here? If you take plus 1, so this is which is nothing but 1 plus or minus 3 by 2. Okay, isn't it? Yeah, correct. So 4 by 2, so 2 comma minus 2, so minus 1. So you are getting two values for L, but one is 2, one is minus 1. But if you go back to the problem, see these are the positive terms. A1 is root 2 and the next term is what? 2 plus root 2. So this is positive and this is positive. Therefore this sequence is converging to positive number only, because if you look at this axis, see I'm starting with root 2, next term will be this one, next term this is a2, next a3 will be this, a4 will be this, a5 will be this one. So therefore this converging to positive number only, it will not come back, it will not come back to the negative side. Okay, since all the terms are positive, the sequence will converge to positive number only. So therefore here what I can say is, so since all the terms are positive, therefore the given sequence converges to 2 only. So therefore it cannot converge to minus 1 here. What I got here? Minus 1. So minus 1 is not possible value, 2 only possible value. Therefore I can take only 2. If the terms of the sequence are negative, therefore the sequence converges to minus 1. Since the terms of the sequence are positive, therefore the given sequence converges to 2 only. Therefore the given sequence an, which is recursive sequence, which is converges to 2. So final answer is 2.